Hello friends, welcome you all to the 14th session of the course. I hope you are enjoying trying out with the simulator, various instructions that you have learned. And let's start with a new concept, though you would have heard about this in your earlier computer organization courses. But as far as ARM is concerned, I will talk about how it is handled in ARM. So this discussion is going to be basically on interrupts and exceptions. In this section, I am not planning to cover how to write interrupt service routines. This section is only to tell you about how interrupts and exceptions are organized and what are their relative priorities and how to take the control to the interrupt service routines. Okay, we will stop with that, and then I will come back after a few lectures on how to write the ISRs. Okay, so that will involve understanding about exceptions, aborts, having a little bit more clarity on that, and then you will be ready to really see a interrupt service routine, how it is written with a real piece of code, and then I will run it through to make the things better for understanding. Okay, very good. So these are the topics that we are going to be covering today. Okay, first we will see what are interrupts and exceptions and how it is handled in the ARM processor. You might have heard both. These words are used without having a clarity on what the difference between these two at times. So I thought I will first clear the difference. What is the difference between interrupts and exceptions? Okay, basically both try to take away the control. Okay, if there are some special kinds of control transfer. What I mean by control transfer, take an example. A PC is pointing at some code, okay, which is in the code memory, and then the processor is keep on fetching the instruction and executing it, and if it encounters a branch, either branch with link or branch, it jumps to that location, okay, and then starts executing it from there. So basically it keeps on executing what it encounters in the code memory, which are some instructions which the processor keeps fetching and then starts executing that. That happens continuously every cycle when the processor is executing. Now these interrupts and exceptions are some special kind of control transfer. That means it takes away the PC from what it is currently doing to some other place. Where do they take away? They take them the control, okay, to some other subroutines which are called ISRs. Okay, interrupt service routines. It is a short form of this subroutine is ISR. This is different from the normal subroutines that you write in your code, which you access it using the branch and link label, right? This label is a subroutine. When the PC, when the program counter encounters this instruction, it jumps to that particular address and then it executes the subroutine there. What happens after completing it? It is returning to the instruction following the branch by copying the R14, because branch with the link would have put the address next to this instruction into the link register, which is the link register. It is R14. So this instruction automatically stores this address in the R14, the address which is next to the branch instruction, branch with link instruction. So it executes this, and then PC is loaded with the what is you have to execute this instruction. Okay, it is not automatically done. Please remember, copying the address into R14 is done by the processor, whereas coming back to the place where R14 is pointing is done by the programmer. You can decide not to come back and ignore the value in R14 and then keep on executing something, that is left to you, but processor always stores this value where the control is supposed to come back in R14. Okay, so this is the normal flow which gets disturbed using the branch with the link, and then the control goes here. But this is all done by the programmer. This is the intent of the programmer who decides how the program flow should go. Okay, this is what we saw in the control flow instruction in the last session. But now what we see as interrupts and exceptions are also changing the flow of instructions, but some are intended and some are unintended. Okay, I will explain what I mean by that. Okay, and some are under the control of the programmer. When it is supposed to happen is whatever you see here, the BL instruction and all that, it is known to the programmer, because the programmer only has written and put a BL here, and then when the execution is coming here, the program is aware that this is going to be executed and the control is going to be flowing to some other place. Whereas when the interrupts and exceptions happen, it happens at a random time. When it is supposed to happen is not known to you. Okay, there may be some reason behind that. It is not arbitrary, but sometimes it is because of some error or some condition it happens. So it is, that is why it's called unprogrammed. You change the flow based on your program, then it is programmed control flow changes. Whereas this is unprogrammed, because when a reset is given to the processor, it's not under the control of the programmer. Okay, CPU's processor is here, reset signal is here. When the user presses the reset button and then the signal is generated, it's not under the control of the programmer. So it can happen anywhere in the program. You can't decide, okay, when I am executing no particular piece of code, maybe from location 100 to 200, I expect this interrupt. You can't say that. Nobody can predict when these interrupts and exceptions are going to happen. But there is one exception to this logic, which I will tell you. That is a software interrupt, which is SWI, that instruction. There you can generate the exception by putting an instruction SWI. Okay, except for that, everything is unprogrammed. Maybe this you can call it as a program, because as a programmer you are trying to put a SWI, which is software interrupt. So through software you are generating an interrupt. That's why it's called SWI. Except for this, okay, everything else is unprogrammed. So let us see. I hope these two are clear to you. Now they alter the interrupt and exceptions, alter the normal program flow to handle external events or to report errors or exceptional conditions. Let us see what do I mean by external events. Let me give you an example, a typical example where interrupts are used. Okay, you know that ARM processor has two inputs. Okay, to refresh your memory, I talked about this sometime back when we talked about the processor. Okay, so the soft core, okay, the soft core of the CPU ARM has two inputs. Okay, this is coming from an external world. One is called IRQ, one is FIQ. What is IRQ? Interrupt request, fast interrupt request. Okay, now don't interpret fast interrupt request means the interrupt faster, and IRQ means the interrupt comes slower. Faster means that this fastness doesn't correspond to the way the interrupts come. It is the way ARM processor responds to it. Okay, the fast interrupt request means this interrupt, whatever is coming from the external world, needs a faster response from the processor. Okay, what I mean by faster response, that means, let us say, okay, a timer is there. Okay, timer is an independent hardware which is counting the clocks. Okay, and then you have programmed the timer to interrupt the processor after counting some 100 cycles. Okay, it could be to, so suppose one cycle corresponds to 1 millisecond in your real time okay, clock. Okay, after 100 millisecond, every 100 millisecond, okay, we want an interrupt to be generated. Okay, This is correspond to 100 millisecond, another 100 millisecond gap. Now, why do we need that interrupt? See, when the processor is busy doing its activities, executing instructions, it doesn't keep track of the time. There is a separate hardware whose job is in the world only to count the number of clock cycles. Maybe it is generated by another crystal and fed to the timer, and then it counts that, and then it interrupts the processor every 100 milliseconds to keep track of some timer count, RTC, real time clock, maybe a 32-bit value, okay, is reserved for counting the time, okay. So it gets incremented every 100 milliseconds. So to do this incrementing, maybe we can have an ISR in the service routine, and then timer is connected to FIQ. So when this particular 100 millisecond elapses, this gives a signal, FIQ signal, and then the processor, whatever it is doing, okay, it stops the execution. When does it stop? After executing the current instruction, okay. Let me tell you, suppose there are pipeline, fetch more, decode and execute. So it is doing some execution. Let us take a worst case of some LDM, okay. You know that lower multiple, maybe it has given, we have given all 15 registers or 16 registers to be loaded from memory. So it is busy doing a memory transaction with the memory. Using the LDM instruction, it is transferring data. LDM is into the processor. How many words? 16 words. Now the interrupt is raised. ARM processor, if it serves the interrupt in the middle of transfer, then it will lose track of how much of data is copied from the memory. So what it does, it completes whatever the instruction being executed fully. Okay, yeah, that means if it has to fetch 16 words from memory, it has to do that, and then after that is done, that execution is done. Okay, there is some other instruction here, some other instruction here, but it ignores all of them. Okay, though it has already come into the processor, it ignores all of them. After this LDM is done, it jumps to some known location. That is what we are going to see how it is going to be done. That we will be covering in this session. So to understand this, where the interrupts come and then how exception happens, this is the way interrupts are generated. You could connect a timer, a hardware unit. Maybe you can connect a serial port. I will be talking about this in the later part of the class. So which is connected to the PC, okay, through a serial port. So its job is to receive your data, and then maybe every data it may respond, it may raise an interrupt, and then the ARM will respond back by executing the ISR. So basically, whenever any external device needs the attention of the processor, it generates an interrupt, and then it is connected to the IRQ or FAQ input, and then processor is already programmed to the way it is supposed to handle that interrupt, and then it will do the job and come back and execute the instruction. So what happens? On IRQ request or FAQ request, it goes to the ISR, executes the ISR, and then into service routine, and comes back and starts executing the next instruction as if nothing has happened. So this control flow, this flow of instruction, though it gets interrupted in between, it continues. Your ISR should be written such a way that it continues without any problem. Okay, what I mean by that, let us talk about it later, but understand the background of this. Okay, that is about any external events. It could be a timer or a serial port. But what do I mean by errors? It could be that when it is fetching an instruction, it has encountered an error. That could be a fetch error. So instruction is being fetched, but the memory is giving an error back, saying that you have reached the end of the memory. Okay, there is no physical memory, but you are trying to access beyond the memory limit. So it depends on the hardware and then how memory is configured, to which address it is mapped. It all depends on those things, and then the memory system may respond back saying that, hey, there is a data about, while accessing a data there is a problem, or while accessing an instruction there is a problem. So based on this, a specific input will be given to the processor, and CPU processor responds back by executing the instruction. So that is what is called exceptional conditions. Okay, let us see more of this. So what is the difference between interrupt and exception? Interrupts are coming from the external world. Okay, it could be a reset given by the user, or it could be generated because of some irrecoverable error. This could be given by the peripherals. Okay, so they are all coming from the external world. External world means it is outside the CPU. Okay, outside the CPU. CPU is okay. I can call it as outside CPU, or it could be outside the processor. If nomenclature is to be followed, processor is ARM, right? CPU is with all the peripherals. So we cannot say outside the CPU because of our nomenclature that we call the ARM SoC. Okay, system on chip. ARM is in this one. Okay, all the peripherals are here. They may generate a IRQ inside the IOS SoC itself. The chip, the interrupts can come, or the reset can come from really external to the chip. Okay, so any of this event. Okay, anyway, it is outside the ARM processor. Okay, a signal is generated by them, which generates the interrupts. Whereas exceptions are the handle conditions detected by the processor itself. Okay, this is the condition detected by the processor, which is executing the instruction. It could be a pre-fetch abort. While executing an instruction, it found that the instruction is not there, or it's an illegal instruction, or the memory is given. Actually detected by the processor with the help of memory unit. Okay, so memory unit only will inform the processor saying that hey, there is a problem in your way you are trying to access the memory. Maybe you are giving me unaligned address, or you are giving me address which is not valid in my memory. Okay, I can only give you, I am a 1 kilobyte memory suppose, and then you are going and it is mapped to some 1000 to 2000 hex. Okay, 1 kilobytes. If you are trying to access beyond this and then you are giving access to this memory, it will give an error because there is no other memory which is mapping to that address. Or it could be a ROM sitting in the chip, in your board. The ARM core is trying to write into ROM memory. You know that read-only memory only you can read from the memory, but you can't write into the memory. By chance, some error has happened and the illegal pointer is trying to write into ROM. Then the memory system will respond back saying that there is a data abort. You are trying to write into me. I am only a read-only memory. So this kind of different things could happen in the system. Okay. So because of that, there will be a error which is caused by some instruction. Okay, being executed by the processor. That's why it's called processor directed, because these are all generated by something which is being done by the processor itself. Okay. So these are all unprogrammed. Okay, I told you this is unprogrammed. This is all these are all unprogrammed. Data about our undefined instructions, they are all unprogrammed. Whereas this is programmed. Suppose you have put an SWA instruction, then this interrupt is generated as whenever the SWA is encountered. So this is known to the programmer, and the programmer has put it intentionally in the program flow. So it goes to the SWA service routine. Okay, we'll see what is done in that later on. So these are the different things about interrupts and exceptions. Okay. Now let us see how it is handled in the processor. Interrupt vector table is a new thing which you are encountering now. I'll tell you what it means. Okay. When an exception or interrupt occurs, the processor sets the PC was to a specific memory address based on which exception or interrupt has happened. The address is within a special address range called a vector table. Okay, assume there is a fixed address location, a physical address location within which different addresses are given, and based on whatever interrupt or exception has happened, the particular address will be accessed by setting the PC value to that address. Okay, it is done automatically by the processor. Okay, we are not writing code for that. The entries in the vector table are instructions that branch to specific routine. Okay, so basically what happens? You take an example. IRQ has happened. So let us give a ARM SoC here. IRQ is coming from the some peripheral. Now the instruction, currently the processor is executing this instruction, assume that it is a LDM instruction for the worst case. Now after the execution is done, after completing every instruction, the processor will check, hey, do I have any interrupts pending for me? Okay. So it encounters, it sees that the signal, it looks at the signal at ARQ and then sees that it is it has become low. So that means that in ARQ is some interrupt is waiting for me. So I am supposed to run the ISR, interrupt service routine. What will it do? The set of actions it will do, but after that, what it will do is it will go to the vector table and then to a fixed location. It knows that in this location only there is a branch to the ISR. Okay, an instruction, actual instruction is put here. So the processor is supposed to just access this address instruction and start executing it. Then automatically the control is taken back to the ISR. Okay, so that going to that location, specific location, is decided by the processor designer. So that is fixed location. So based on that it goes there. So that is being done by the processor. Okay, very good. 1 second. Okay. Now the memory map address 00 is reserved for the vector. Okay, and then 4 bytes each for every instruction, every interrupt. So one instruction only can be put in 4 bytes. You know that. Okay. When an exception or interrupt occurs, the processor suspends normal execution, as I told you, and starts loading the instructions from the vector table. Each vector table entry contains a form of a branch instruction to the pointing to the start of a specific routine, which is an ISR, interrupt service routine. Okay, let us see how it is done. So these are all the addresses. Okay, 00 is reserved for a reset vector. Okay, whenever a reset happens, the processor will come here and then access the instruction stored here, which is happens to be a branch instruction. Similarly, other undefined instruction, if it encounters an undefined instruction or FWI. So these are all the different interrupts, and then these are all the different addresses where it accesses the particular instruction stored for handling these various vector interrupts and exceptions. So you know that there are different modes in the processor. So this is called supervisor mode, this is undefined. Okay, this is also for supervisor mode, abort mode, and IRQ mode and FIQ mode. So what is the relevance between these exceptions and the mode? Please remember the register bank discussion we had. Let me recall that for you. You know that there is a user mode and system mode. Okay, so there are 16 registers and then you have a CPSR, correct? So these are all accessed by the system mode or user mode. Okay, user mode is the lowest privilege mode, and system mode is a privileged mode that it can change the mode bits in the processor CPSR. By modifying this, you can change to different modes. Okay. Now you know that register bank, right? FIQ, there is a register bank. You can go back. Some set of registers are reserved here in FIQ. This will become visible when it is in FIQ mode, and there is a stored program status register (SPSR). Please remember that physically these registers are there and these registers are there, and this is also there in those modes. Okay, though it is available all throughout the processor, but it will be visible and you can access them only when you are in that mode. So let me erase this. Okay, it is too much. Okay, so maybe a small one, R14 and R13. Okay, if you recall, I want you to go and see these different modes. Okay, this can be IRQ mode, and there are abort. Okay, similar thing. Okay, and then we have supervisor. Okay, SVC mode and undefined. Okay, so these are the different modes and different registers are available. So this is indicating that which mode the processor enters on receiving these instructions. Okay, So automatically this is also modified by the processor, and I will explain these things in detail, but this is only just a recap of the register banks. You have to remember this, for the, especially to understand the abort instructions and all that, you should have this register bank in your back of your memory. Okay, fine. When exceptions arises, ARM completes the current instruction. I told you as best it can. What do I mean by as best as it can? I'll give you an example. Okay. I always like to have an interrupt when LDM is being executed, because that's the worst case scenario, and 16 registers are getting loaded from memory to processor. Okay, sorry, this is the memory only. Okay, this is instruction. So I'm sorry, 16 to CPU. Okay, it goes to CPU. Now what happens? Suppose if this accessing this instruction, this data memory itself, if there is an error. Okay, so maybe halfway through it encountered an error, then it cannot complete the instruction before the data abort happens, because while accessing this data only the exception has happened. So it cannot complete. I told you that when interrupt happens, it will complete the current instruction in execution, and then only come and respond to the interrupt. But that is not always true. If it is coming from external world, it is nothing to do with the instruction being executed, then you could afford to do the completing the instruction and then come and respond to the interrupt which has come from the external world. But if the exception itself is due to the instruction being executed, maybe a instruction fetch or instruction data abort, you cannot wait for this to be completed, because that itself is causing the issue. So it will be immediately responded to. Okay, that is what I am saying, as best it can. If it can complete the execution, it will do. Otherwise, it will immediately respond back. On receiving reset signal, okay. Suppose you are executing a LDM. Okay, again on my example, LDM is being executed. You have the memory, from memory it is transferring some code to the CPU. Okay, it has only transferred some 4 words. Okay, from the memory, it is supposed to access few more. That means 12 more. But the CPU is here, right? The reset signal has come. Okay, somebody has pressed the reset signal. Imagine it could come at any time in the cycle, so it could happen while just 4 words have been transferred. So when the reset signal happens, that is something to tell the processor that enough of what you are doing. Okay, there is a catastrophe. You have to reset the whole system now. Okay, that means whether you are executing any important instruction, or maybe you are executing some data abort, or you are executing something, processing some timer interrupt, doesn't matter. Reset is the most highly valued or highest priority interrupt. That's why it is sitting at the top. Okay, so by chance it is there because of the 0, but I will show you the priority list where the reset will be at the top. So when the reset happens, the current instruction is not completed. It will not wait for this current instruction to be completed. It will just come out of the execution and then start accessing the instruction from this location, and then do whatever is to be done on reset. Okay, I will tell you what is to be done on reset. I can just tell you some few things. Okay, so normally the vector addresses will contain a branch to the relevant routine. Okay, I told you, but though FIQ routine can start immediately. What I mean by that, maybe you will make it. It will become clearer in the next slide. See, FIQ vector is here. Okay, end of, these are the possible exceptions and interrupts that can happen, and these are the locations where the specific address is reserved in the memory for putting the branch instructions to the ISR. Okay, this will jump to FIQ ISR, this will come to ARQ ISR. But here if you see, after one see the address, IR addresses, there is no reservation. Okay, it could be used by anybody. So FAQ, as I told you, that is this has to be responded to faster. So if you put a branch instruction, it will be again flushing the pipeline and then go to the ISR. So it will take more time. So you can start your ISR itself here in this location. Okay, I will explain you in the next slide. So that's why FAQ is kept in the end, so that you can start your routine immediately. So this is the typical memory. So I am giving the lower address here and a higher address here. So all the lower addresses are reserved here. After this one C, there is no specific reservation from the processor perspective. So you could write the FIQ interrupt ISR itself here without jumping. That's what I mean by writing it here. Okay. You can even have a code or data, anything stack or whatever. No, I missed the stack. So please don't think that only core data is there and stack is somewhere. Everything has to be within this limit. Okay, this is 32-bit address limit. So everything is given in hexadecimal. So this is the maximum address that the ARM processor can access, ARM 7 TDMI, and within this, let me put stack also here. Okay, you have to reserve stack space also here. Okay, very good. Now you understood. So what is in each of these vectors? Branch to this, branch to this, branch to different handler. Okay, ISR or handler or synonyms. Okay, you can use any of them. Now you may wonder what is this no op sitting here in between. See, this is some backward compatibility. This is for the earlier processor when there were 24-bit addresses were supported prior to ARM 70 DMA. There was some exception which was used for illegal address generation beyond 64-bit. So it is no longer valid. So from we are starting from 7 TDMA, so please ignore this particular vector. This is not handled now. Okay, very good. Let us go to next topic. Now this is a typical example how a code and data is. Please remember that stack is also here. Okay. Okay. Sorry about the handwriting. It is actually stack. Okay. You have to believe me. Okay. Now vector table is here. Vector table is expanded here. Okay, this is the expanded version of what is shown here, and then you could keep anywhere the reset init code, okay, or SCC the supervisor code ISR, and then code and stack can be here, and FIQ ISR can start immediately. Okay, so it is free. You can free to locate it. Now, how you may wonder how do I decide where everything sits? You have to use the tools. Okay, the tools coming with the ARM processor, not only the compiler and assembler, locator, linker, okay, loader, all the tools are there which will help you to mention where you want to keep any of them, and then you will be mentioning some OR, or based on the assembler syntax you may define exact location of where your service routines or data should be sitting. Based on that, the linker will place them all, and then the code will run on the processor. Okay, so let us not worry about them now. Assume that they'll be taken care of. Okay, good. So this is how when an interrupt happens, the control comes here to the particular based on the. See, you may wonder how does it know which interrupt? It is very simple. If IRQ is there on the signal on the input pin, then it knows that IRQ has come. If it is a input has come from FIQ, it knows that FIQ is generated. Or if it is a fetch abort, it will know that when memory is saying that there is an abort, okay, memory is giving back an abort, and then it knows that which cycle was going, whether instruction was being fetched or data was being fetched. So it will know that it is because of which data abort or fetch abort, refetch abort. Or if undefined instruction is encountered, it will know. So SWA is there, then it will know that it's a software interrupt. So it knows which has caused this interrupts or exception, and based on that, processor comes to the predefined address and simply fetches this instruction and then gives you to the pipeline. Then pipeline takes care of taking it back to the ISR and then start executing whatever you are writing in the code. Okay, I hope this is clear to you. Now various types of interrupts. Okay, though I have explained something, let me formally explain that. Okay, this is the reset. Okay, points to the location of the first instruction to be executed by the processor on reset signal. It could be some because of on power on. Okay, please remember when power on happens, what is first executed? The reset. It generates the reset. Okay, and then the processor jumps to the reset location, and then init code is executed. After that only anything happens. So the processor branches to the initialization code. Please remember on reset, power on also the reset is generated. Okay, or it could be generated internally by some circuitry based on some observable error. Now what is undefined instruction? Sorry, So undefined instruction is exception is raised when the processor cannot decode an instruction. So let me define it here only. Okay, assume that this is the ROM. Okay, where code is there in the memory. Okay, code is put in the ROM. ARM is here. Processor. It is accessing the code, giving the address and then getting the code and then executing them. Suppose if it goes beyond this, what happens? It will give a either illegal. It will give a prefetch abort. Okay, or if suppose a memory is corrupted and then it gives an instruction which is not understandable by the processor, then also an undefined instruction exception is raised. Okay. Software interrupt, whenever it encounters the SWA instruction, it generates the software interrupt. So it's basically used for operating system routines. So basically, whenever you want to call some fixed routines written by the operating system vendor, you can plug in the code here, and then SWA will be taking that control to the SWA ISR. So basically, if you want to transfer the control through a OS to a controlled manner, then this can be used. Okay. Normally, this is how it is being used in the typical program. Now, prefetch abort I explained you earlier. Okay. If suppose you are trying to access the area without, so you may not understand what I mean by access permission. You will understand when I have explained you MMU and memory protection unit MPU. Okay. So till then, please keep your inquisitiveness, the background. We will cover it later. So there are some areas in the memory which can be protected by not to be accessed by the user routine. Okay. Suppose you are in a user process and as a user we might make a mistake in writing the program and then try to access the area which is not our within our limit. Maybe it is a OS area. Okay. OS code is here, or maybe OS data is here, and then through a wrong data manipulation you are trying to access that. What happens? You may corrupt the OS operating system. So to prevent it, the memory protection unit will be trying to see whether you have enough access permission to access these addresses. It will be accessed only when supervisor mode is there. If we are running it in supervisor mode, it may allow you to access it. How will you go to supervisor mode? You will execute SWA. So SWA is a controlled mechanism to access the OS code. Okay. So if it is accessed using the OS code, then the OS code knows how to access its data and what to do with the data, OS data. But our user program may not know that, and it may corrupt it unintentionally or intentionally. So to prevent it, there are some memory protection unit and other hardware units are there which will continuously be monitoring what is being accessed and which mode the processor currently is in, and then whether it has enough permissions to do the job. Okay, whether reading or writing. So based on that, it may give a abort. So when the contents of that virtual address is not available, so this is another in the case of where you have virtual memory. Okay, that memory is not brought into the RAM, and then your code is accessing it. Then it will say that this code is currently not in the memory, it is in the hard disk maybe, or it's in the flash. So it has to be copied into the RAM and then given access back to the processor to run the code. So this will also be clear when I talk about physical memory and virtual memory. So I will give you the background. If you are already aware of this, you can understand what it means. Otherwise, don't bother. We will anyway touch on this later. So the actual abort is handled only when the aborted instruction is enters execute stage. Okay. So what I mean by that? See, I told that suppose a LDM instruction or LDR instruction or SDR instruction, something to do with the load or swap instruction. Okay, what all instructions can cause? These are instructions can cause a data abort. We are talking about prefetch here, but what I am saying is in the prefetch case, suppose an instruction which is maybe one of these instructions. Okay, when you are accessing that when you would have got the abort actually when you are in the prefetch mode. Okay, that time itself the memory would have said that, hey, I am not able to access this instruction you are interested in, but the processor knows that there is a abort, prefetch abort has happened, the memory has given the error when I try to access this instruction, but it will not it will not execute the abort ISR or the exception handler in this case, here itself, in this clock itself. Please remember, it has happened in the prefetch case. Okay, currently some instruction is getting executed here. Okay, this will not be affected. Okay, it will carry on, and then the decode in this, what it will do, the processor will make this as a invalid, this instruction is invalid, and then some prefetch instruction exception has been caused in when I was trying to access this instruction. It will leave that information along with the instruction. So through the pipeline registers, it will pass on that information. Okay, so this instruction will be executed, the previous instruction, and then the instruction after that will also be executed, and then when this comes here, then only the exception happens. You may wonder why it is delayed. Anyway, I know that it has happened here. Why should I delay it? You think it over. Maybe I will ask this question and then we will clarify that why the prefetch abort has to be delayed. Please remember, if you don't understand this, I will explain again. Prefetch abort is what? It is a happens when the prefetch, this is pipeline I am drawing. Okay, please remember, this is the pipeline. This is a fetch mode, fetch stage and decode stage and execute stage. Prefetch abort happens when I am trying to access an instruction. Okay, let me explain you a set of instruction being executed. Currently the PC is executing this instruction, but when this was accessed, okay, the abort has happened. See, assume this is 100, again 104 and 108. When it was successful 108, the prefetch abort has happened. So immediately it won't be generating an abort. What I mean by generating an abort? Going to the abort handler, accessing that particular vector table, and then going and executing the ISR. Okay, the data about prefetch abort ISR. It will not happen immediately here, so it will complete this execution successfully if it can, and then this will move here, this will move here, but it will indicate that this is invalid. Don't try to execute this instruction. I encountered a problem when I tried to execute, fetch this instruction. So please, when you get a chance to execute this instruction, call this ISR, prefetch abort ISR. So when this instruction 104 comes here, it will also be executed, and when this 108 comes here, immediately the abort will be raised. Okay, think it over why it is delayed. I will explain you later. Now data abort. Okay, data abort, when can it happen? When you are accessing a data. When will you be accessing a data? Will it happen in the prefetch? Will it happen in the decode, or will it happen in the execute stage? Please think it over. When will the data abort happen? Okay. Suppose I said when you are doing a LDM instruction, yeah, data abort can happen. Okay, but this LDM instruction can be in 3 stages, right? Given an instruction, it will come to prefetch stage, and then it will be in decode stage for some one clock, and then it will come to execute. When will the data abort happen actually? Can it happen here? Here only the instruction is getting executed. Actually data is not accessed. Please remember, accessing an instruction is different from accessing the data. This LDM instruction itself is accessed here, but actual data transfer happens when? Will it be in data mode? Decode mode? It can't be. Decode mode only generates all the decode signals what is required for the execute stage to take care. So actually when LDM comes here, when it gets executed, that time only it is actually going and doing what is requested by the instruction. So it says I am interested in accessing some registers, some memory. Either I want to write into the memory or read from the memory, something I am telling in this instruction. So the processor is going to do that, and during that time the data abort can happen. So data abort can happen only when the data access happens, and data abort access can happen only in the execute stage of which instructions? Tell me what are the instructions can cause data abort? Oh, very good. LDR. Can STR have also can generate? Of course, it can. It can be a LDR is a read abort, read from memory. STR is a write to the memory. Can LDM and STM can cause the data abort? Of course, it can cause. Can you think of some other instruction apart from these four? Okay, if you have it in mind, do you think this can cause a data abort? What does it do? Swap. Swap does the exchange of data, right? It reads the data and then writes the data. So there is a read, memory read, and there is a memory write. So it can cause a data abort. Agree? So swap can cause. Now I'll ask you another question. Can the thumb mode you are not yet aware, so I can make a statement that these aborts can happen both in ARM mode and thumb mode. Please remember. Okay, doesn't matter which mode it is. Maybe the bit of the data code access may be different, but it can happen in both the modes. So these are the ways a data abort can happen. Okay, in thumb mode there are other instructions which is not listed here, so I will not confuse you now. But please remember these are the instructions. Are there any other instructions which access the data in the memory? I don't think so. If you remember, let me know. So these are the instructions which cause. So that also happens only when they are in the execute stage of the pipeline. Please remember that. Okay. So when the contents of the virtual address page is not available, so again MMU related stuff. So keep in mind it could happen because of some page missing. We will come back to this. So whenever an instruction data abort, okay, especially when data abort happens, the abort handler does something, okay, recovers the instruction, tries to execute the same instruction again. That is what I am saying, restarted. Suppose LDM has caused a data abort, so I told you that it will come in incomplete instruction, it will be incomplete, and then it will come to the abort handler. Abort handler does something and then comes back to the same location to try executing the instruction again. Okay. So it is maybe because of some memory is not available, some page is not available, so it can be recovered and then the same instruction can be tried out. So that's what I am saying, restarted. The same instruction can be restarted. So you have to know the abort handler has to save the proper value to come back and execute the instruction. Okay, that is in the hands of the handler. Okay, handler only has to decide where it has to come back and execute the next instruction, whether in a same instruction or the next one is decided by the handler based on the situation. Okay, interrupt is used by external hardware. So, but which instruction will be executed when you have this? Okay, interrupt. Okay, let me explain. You have a processor here. I told you that interrupts are coming from outside world, IRQ or maybe FIQ. It is executing the code. Now I told one difference between abort and interrupt is whatever is being executed is completed and ISR is responded to. What I mean by ISR? Responded to, vector table is there, interrupt vector table. It goes to the IRQ or FIQ to the handler. Okay, handler gets executed or ISR, and then after handler getting executed, it returns, the control returns back to the instruction which is next to the previous instruction at which the interrupt happened. Okay, so this is completed. Anyway, I said that when interrupt happens, the processor completes the execution. So it is supposed to now execute the next instruction. As if nothing has happened, the control flow should carry on with what it was doing. So after the handler, it should come back here. So please remember to handle the interrupt. After the handler is done, the control comes back. You are supposed to make the controller come back to this next instruction. Whereas in the exception handler, you may decide to come back to the same instruction. Okay. Why do you think on interrupt you have to come to the next instruction? Because you don't want to execute the same instruction again. Okay. If you do it again, the behavior will be totally different. What the programmer intended and what happens will be totally different. Second example, suppose you have put a instruction called add R1, comma immediate 02. Okay. this was the instruction which was being executed and interrupt happened. Now R1 has been added with 2. So R1 was having some value earlier 10 and then it has become 12 now. It has executed this instruction and then went to interrupt. Now after the interrupt, if it comes back to the same location, what will happen? It will get implemented again, which was not intended by the programmer. So you should not execute the same instruction when interrupt happens. You should come to the next instruction following this. Thus the normal flow happens. Okay. So please remember that. So that's the way interrupts are handled. Okay. And then it can only be raised if IRQ. Okay. One more thing is, if you remember, there was a CPSR register. There was a 2 bits. Okay. I think if I remember 0 to 5. Okay. Is mode bits. Okay. And then some mode bit, T bit, and this is FIQ bit, and this is the IRQ bit. This is bit 0, bit 6, bit 7. Oh, sorry. Okay, this is 4. Wrong. This is 4, this is 5, and this is 6, and this is 7. Bit 7. That means 8 bits. Okay. So if this particular bit in which one? Which register? CPSR. Okay. If this bit is 1, that means even if FIQ signal is given to the processor will ignore it. I don't care about that interrupt. I will continue with whatever I am doing. If it is disabled, if it is enabled, then the interrupt will be processed by the processor if the signal comes. Okay. So you can control the whether to respond to interrupt or not by setting this bits or clearing the bits. So that's what I am saying. It will be right if IRQ and FIQ are not masked in the CPSR. Okay. I hope it is clear to you. Let us go. Now I explained you already. Okay. What are the different modes of this different exceptions and interrupts? So reset executes in supervisor mode, and then SWA also software interrupt or reset both execute in supervisor mode. Abort both prefetch and data abort goes to abort mode. FIQ is FIQ mode, IRQ mode, and undefined there is a separate mode. So why I am very particular about saying these things? Because you should know that which bank will be visible on which interrupt. So if you remember, FIQ mode has more registers in it. FIQ mode. So that means you don't have to save those registers because new set of registers are I registers are visible in the FIQ mode. So you can use them freely without getting worried about the user mode previously. Whatever was the register, those registers will not be impacted when you are using this in those modes. I will explain them clearly in the when I am handling the abort handler. Right now, this is what it means. Okay. Very good. Now relative priorities. These are the relative priorities. So reset is the highest priority. So I told you that even if any instruction is getting executed, it won't be completed. The reset will be answered immediately. So this is more important. And data abort is the next higher priority, and FIQ, IRQ are the priority wise. So what do I mean by the relative priorities? The relative priorities of exceptions are given above. Multiple exceptions interrupts can happen at the same time. Please remember, it is not that anybody outside the world or the instruction being executed are aware of anything happening with the other part of the things. So IRQ is happening independent of IRQ event is happening independent of FIQ event. So they can all happen at the same time. That is the worst case scenario. So the abort can happen also simultaneously. So everything can happen together. Okay, but some things are mutually exclusive. Which are mutually exclusive? A prefetch abort and a data abort, can it happen together at the same time? See, remember, a memory is accessed, right? Either data is accessed at a time, you agree? It's on an architecture, right? Or a code is accessed, prefetch. The memory, when you are accessing it, either you are doing a data access or a code access. So when will the actual abort happen? During the actual, the memory unit MMU, memory or not memory system informs the CPU that hey, there is an abort. So that abort signal is generated based on either a memory read or a write. It could be for data or it could be for code, but it cannot happen together, right? So they cannot happen. The event cannot be generated by the memory for both. Okay, so that's what I'm trying to say that. But something during this time an IRQ can come. There is no relationship between when IRQ is generated and when abort has happened, or the processor may be executing SWI instruction and that time a FAQ can come. So these FAQs, IRQs and these aborts can all happen together. So when these things happen together, how will the processor know which one to act on first? Because I told you that there are vector table and then the processor can do only one job at a time. Okay, it can access either FAQ handler or it can go to the IRQ handler or it can go to SWI handler. It cannot go to everything. So it has to resolve at that particular moment a clock. Which one should I look at? So it is actually hardwired. Okay, the priority of relative priorities of each. So the processor knows when there is a reset signal given, there is a data of what happening, and FAQ happens and IRQ happens. It will honor this. Okay, it will ignore them all. Okay, sometimes if reset is not there, it is other things are happening. It will not ignore them. It will wait. These aborts will wait, and maybe the first one will be acted upon, and then after it is done with that job, it will come and act on this and that on this. So there will be some sequence followed. So that sequence is what is given by the priority given here. Okay, that's why what I mean by relative priority. Or while one is being handled, another one might happen. Please remember, when it is in FAQ handler, a reset can happen. Nobody can prevent it. Or even FAQ handler itself, okay, FAQ handler is doing a memory read and it creates a data abort. Or it is fetching the handler code and it results in a prefetch abort. So while one exception is being handled, another one can be generated. So during that time, this relative priority will resolve how the processor is supposed to respond to. So if during this FAQ data abort happens, it will respond to it. Whereas if prefetch abort happens, it will wait for. Okay, it's a very mixed thing. Okay, here though it's low priority, if you are not able to access the code, you cannot complete the handler. So it will know which one to respond to. Suppose if it is IRQ handler interrupt has happened when it is being handled, it will not respond to IRQ until the handler is done with that, and IRQ will be enabled and then it will do. So these things I will explain you in detail when I am handling the how to write handlers for all of them. Okay, but have this idea in background domain. It will help. Lower priority exceptions are handled only after the high priority exceptions are handled. Okay. Now I am just going to give a brief idea about how to call, how the handlers are called. Okay, from the interrupt vector. Okay, interrupt vectors are there, and then you are calling the handler. I told you, right? This is vector table, and then by each location you are calling the handler. Now, what is the instruction you are supposed to put? I showed you some branch instruction, but there are different ways you can pass the control back to the handler. Control. So there are number of ways an execution can be transferred to start the interrupt handler using one of the instructions in the vector table. See, how many instructions can be there? Only one instruction, because if you recall, the vector tables are all only 4 bytes are reserved for each other. So only one instruction can be there. So you have to transfer the control to the handler in one instruction. You can't have multiple instructions. Then you will be writing into the adjacent neighboring vector. So that is not correct. So it is one instruction. So this you are aware, a branch instruction. Okay. Is it required? Link. Okay. We will not worry about this now, but you will not normally use the link register here. Just a branch. Okay. You don't want to come back. Okay, I'll explain you why BL is not normally used. This is a vector, IRQ vector, suppose. Okay, you are free to use B to the handler, branch to handler, or BL to handler. BL to handler means what? You will say that the next instruction I will put it in the link register, right? But in this case, you are not executing a normal subroutine flow, right? Then you want the control to come back after the subroutine is called. Here is an interrupt. So you don't want the next vector, one interrupt happen. You don't want to execute all the service routines of other interrupts. So you will not put a BL, you will put a B, and anyway this interrupts are handled in a different way than normal branch to link. Okay, so you can have a branch instruction to come to handler. That's why I mentioned a branch instruction, not a branch with a link instruction. Okay, so you can put a move instructions also. So what I sorry. Okay. See, how do I put a move instruction? So I can say move PC, comma some location. Okay, I can put a byte address. Okay, a byte shifted value. If you recall the instruction format I have mentioned, you can mention a byte value. Okay, which will be rotated by if you suppose you have mentioned it 4-bit value, and then it will be multiplied by 2, and then that many rotation ROR will be done, and then that particular value will be loaded into the register, right. So there was a instruction, byte shifted instruction, even number of bits it will be rotated. So that you can use if you can place your handler in a fixed location, then that constant can be, if you can generate that constant you can use that. Otherwise we may have to use a different instruction based on where the ISR is located. Otherwise you can use LDR. LDR is with respect to PC. See, it is very simple here. See, current PC anyway, if you are IRQ vector, what is the fixed location of IRQ vector. So that PC value, current PC value, or maybe it will be, because of prefetch it may be +4 or +8. Okay, yes, it will be +8 anyway normally. See, please remember the prefetch doesn't know whether it is accessing the interpreter or not. Once this branch, whatever you are writing here, this instruction is put on, it will start doing that same +4 +8. Okay, so when it is doing it, you will be able to, based on the PC value, you can put the offset and then locate it somewhere closer to the current PC. That's why I told you that ISRs are written very close to the vector table. Okay, so that plus or minus 32 anyway, you have 12-bit offset, so it is a little lower than the 32-bit range, but you can anyway access the code. Okay, so you can, with respect to PC, you can add an offset. Why only add is mentioned here? Because anyway already in this vector table is at the lower address, so you can't go below this, right? You can't go below, so you have to go up only. So you have to put a positive offset only, which will be sitting somewhere in the memory higher than the vector table. Okay, so you can use this instruction also to transfer the control to the handler. Please remember, these are the instructions which can be used to transfer the control from the vector table to the handler. That's what I am trying to say here. Okay, very good. Now what all things the processor does when it is handling the exception? The current instruction being executed is completed. I told you that. If the current instruction is a multi-cycle instruction, it is completed before responding to the interrupt. It doesn't matter whether multi-cycle, whether LDM or LDR, it doesn't matter, or just an add, doesn't matter. That instruction will be done. Please remember, when there is an exception or interrupt, you don't have a control on which instruction is being executed at that time the interrupt or exception happens. Okay, especially interrupts, you don't have a clue when IRQ will be generated or FAQ will be generated. You don't have any clue. Okay, when which instruction is executed. So any instruction could be there at the time where the IRQ happens. So but the processor will sincerely execute this instruction fully and then only look at the IRQ or FAQ. Okay, that's what I am trying to say. So if you want to reduce the latency, what I mean by latency, suppose the hardware, I told you the timer or a serial port is generating an interrupt, it would have generated at particular time t, assume that it is t is equal to 0, that is our clock starting. Okay, but the processor will take its own time, sweet time, because it is currently executing this LDM instruction, which is a 16 words of transfer. So it will complete it, and then only it will realize that, oh, there is an IRQ which has come in. So let me go to the vector table. Okay, and then let me access this branch instruction or move whatever you have put in, and then go to the ISR. So there is a finite time elapsed from the time the signal, actual hardware signal of IRQ or FAQ has been generated, and the time at which the first instruction of the ISR is executed. Okay, so it has to wait for this current execution to be done. Then it has to do some saving of some values, which I will explain you, and then access this instruction. It has come to the pipeline and then gets executed. Then only it will come to the ISR and then fetch the first instruction and then start executing it. So lot of time is elapsed, and that is the called interrupt latency. So this clock cycles, how many clocks it takes for responding to an interrupt, means how responsive your system is going to be. It is like when I say that there is a fire alarm and I have connected the fire alarm to FAQ, okay, and this ARM processor, your embedded system, is supposed to switch off the remove the control to all the access to the door, and then switch on the fire extinguishers so that fire extinguishers are activated, and then switch on the alarm so that there is a hoot sound so that the incumbent, the people who are inside the office can escape or take action on the fire. Now that time how important it is to have this latency to be lower. You can't take few seconds or even to respond to this and then activate all these alarms and then inform the people who are in the building. So the latency is very important. So especially when there is a controller which is controlling your car engine or it is controlling your brake system, it has to respond in a few microseconds or preferably much earlier than that. So the number of clocks decides how fast the processor can respond to your external events. So you have to take care of it when you are designing your system accordingly. Data about generated if LDR or SDR is encounter a problem, which I explained you already. Okay, we will have a detailed discussion on this later on. Now one more point I want to highlight here. When these different aborts are happening, what happens to the IRQ and I bit? I mentioned to you in the CPSR there are two bits which are maintained. If you remember, bit 7 and bit 6. Okay, now I remember it. So this is FAQ bit and this is the IRQ bit. Okay, so these bits are set. That means those particular interrupt is disabled. So when reset happens, both interrupts are disabled. Okay, so please, once reset is the highest priority and then you have to do a recovery. So all the aborts, all the interrupts are disabled. So IRQ is FAQs are disabled. Whereas if you are processing a data abort, though it is higher priority than fast interrupt is not disabled. It is this is not disabled. It is enabled. If you are in the FAQ itself, you are processing the FAQ, then FAQ is disabled and IRQ is also disabled because it is a higher priority than the FAQ. So that is disabled. If you are in IRQ, if you are already servicing in IRQ, the subsequent IRQ is disabled. Okay. Similarly, if you are here, okay, the I bit is set. Okay, when you are into the abort. So inside the ISR, you may have to handle this and then enable them based on the priority. Okay, so that I will be explaining you later. But this is how the default the processor does it, and then ISR handler should undo it after taking some action. Okay, to performing some operations in the abort handler. Okay, so when an exception is raised, disabling of IRQ FAQ is done automatically by the processor on entering the exception handler. Okay. So what all the code does? The CPSR is saved to SPSR mode. What I mean by that? See, you are assume that you are in user mode executing our user code. The IRQ happens. Okay. Then this current execution is done, and then the next instruction is to be fetched, but it is to be executed, but it doesn't execute this instruction. It goes to IRQ handler. So while doing that, it has got a CPSR, right? So when I say that when you come back after the ISR is executed to this location, okay, next instruction, it should go as if nothing has happened in between. Okay. when you are executing this instruction, after that this instruction, but in between the ISR has come and then you have come back from there. If you don't want any impact of that, then you have to make sure that CPSR is also not disturbed. Why? Because you have in ISR you may write a move s, okay, you may do a add s, which will impact the CPSR flags, okay, or you may do some other operation which will impact the mode bits of the processor, okay, because you are going to IRQ vector, that means the user mode to IRQ mode you are going, so the mode bits will be affected, so condition bits flags will be affected. So this I would know as a user I don't want this to be impacted at all because of some interrupt coming in between. So how does the processor take care of it? It knows that there is a stored SPSR available in that mode to which it is going. It copies the CPSR into that. So after you handle the ISR, you restore it back. Okay, you mean the handler copy the SPSR of that mode to CPSR and then pass the control to this location. Now you see, as if nothing has happened. The code is executing now. The flags are same as how it was earlier. So from the programmer perspective or from the user the program perspective, there is no impact of this interrupt happening. That will happen only when the CPSR is saved and restored back after you come back from the ISR. So it is very important to save them. Okay, that is what the processor does. I will explain the reason for that. I hope it is clear to you. One more simple thing you should remember is, it is always the exceptions are handled in ARM state. Again, you don't know the ARM or thumbs mode, means ARM, the exceptions are handled at 32-bit instructions. Okay, that's all, simple. It doesn't treat them as 16-bit. Always the exceptions are in ARM mode. And then it does the CPSR, because you saw in the previous slide I showed that IRQ is disabled in all the exceptions. So it disables IRQ. It disables FAQ if it is FAQ or insert, and all other places FAQ is not disabled, because we don't want a fast interrupt to be disabled, because that is more critical interrupt is attached to that. Okay, as a system designer you are supposed to make sure that FAQ is what is connected to a critical module. It could be a timer or it could be a sensor. Okay, this is ARM. So you have to make sure that FAQ is connected to the most critical interrupt module, which will indicate to the processor that hey, please take immediate action. So that's why FAQ is not disabled until except for FAQ and reset. And then one more thing is, I told you that it will come back to the location. How will it come back? Until it saves it, right? This PC value, okay, R15 is saved in the LR. See, it is not actually saving this instruction, it is +8, because when this is executed, PC would have advanced to +8 already. Okay, please remember, it would have already gone to +8. Okay, so this PC value is stored in the LR. LR of what? LR of that particular mode. If IRQ is the cause of the interrupt, you know that there is a bank R13 and R14 of IRQ mode. Okay, in that LR, the R14 is LR register. So of that mode, okay, of that mode, the value who does it? Processor does it. It stores the current PC value into that. So the handler has to remember this and then come back, load the PC back with this value, so that control comes back to the code which was being executed. Okay, it should adjust it such a way that it comes back. So it will become clear to you when I am explaining about. But remember, this is what done by the processor. Okay, these steps are very important. Please understand this, read out, and then make sure that you understand this properly. Okay. So it sets the CPSR to the exception mode. So it saves the CPSR first, which will have the old mode what was there, and then it changes the CPSR, because current mode is controlled by the value in CPSR. Please remember, the current mode of the processor is controlled by the mode bit here, not on the SPSR. Okay, SPSR is visible based on which mode you are in, but the mode bit here doesn't have a control on the processor's status. So processor's mode status is controlled by the mode between CPSR. So what you do is current mode you copy into the SPSR and then change it so that to reflect that you are in the IRQ mode or FIQ mode. Okay. And then PC is addressed the exception handler. Now interrupt vector table that 0 to C, one of the addresses will be loaded into the PC so that the control goes to that location. That's all. With this, I think we are done with most of the discussion. So let us see whether you are able to understand this quiz. Take a 5 minutes break. Okay, come back. Okay, welcome back. Tell me what happens. What is the all exception interrupts are handled only in ARM state? I told you that it is all handled in ARM state. Why? Are you clear with the answer? Though you don't know about ARM, you know that it is a 16-bit. No, thumb mode is a 16-bit instructions. So the answer is D. Okay. The reason being, please remember, the vector table is only one in the processor. Okay. Vector table is only one, which is at the location from this 1 0 to C 1 C or whatever. You have as a programmer or as a system developer, you have to fill in some instruction here. Agree? So that branch instruction, whatever you are putting or move instruction, you have to decide whether you are going to put a 32-bit or 16-bit. Because if it has to be supported in thumb mode, you have to put a 16-bit instruction. So when you have only one place, and then you have to put the branch instructions here based on which interrupt is happening. One thing you have to remember, when the interrupt happens, okay, IRQ or exception or whatever happens, you don't have any control on which instruction is being executed by the ARM processor. Not only that, you don't have a control on which instruction is executed, you don't have a control on which mode it is in, whether it is in ARM state or it is in a thumb state. It may be executing a thumb instruction or it may be executing an ARM instruction. ARM instruction means 32-bit wide, thumb instruction means 16-bit wide. That's all you have to know. So through some means of CPSR, you have changed the mode of the processor and it is in thumb mode. It is executing 16-bit instruction. Now interrupt happens. Now suppose if you say that I want every ISR handler or the record table, it should be independent of ARM or thumb mode, then what happens? Suppose ARM processor continues to be in thumb mode, okay, and then tries to access the vector table. It will interpret this instructions as a 16-bit instruction, isn't it? It won't interpret it as a 132-bit instruction. Then what it will conclude from it? Something else, not what the programmer intended. So that's a confusion, right? What you store here, you can decide to put either 32-bit instruction or a 16-bit instruction. You can't have both. If you want to have both, you have to change it. Whenever the mode changes, you have to come and reload it with something else, which will be time consuming and it's not suitable for a real-time system. Or another option is reserve one more table, which will be a 16-bit mode table. Okay, that's another option. But so the processor will not, I am in thumb mode, so let me go to this vector table and then access this. Then what happens? This handler also should be in thumb mode. So effectively you will be managing two things, both handler as well as vector table, and lots of confusion, right? So and it is actually impacting the performance of the system. So ARM, rightly decided, the designers, that all the exceptions, interrupts, everything will be handled in ARM mode, irrespective of whether the current mode of the processor is 32-bit or 16-bit mode, on thumb mode or ARM mode. That means it will remember, because you are saving the CPSR into SPSR. So that CPSR has a T bit there. So you can come back after the vector, after the handler is done, you can come back to the previous mode that you are executing. So the thumb instruction or ARM instruction, it will not get impacted at all. Please remember that. Only thing is, when it is jumping to the handler, it is in the ARM mode. Whether it was in thumb mode or ARM mode, both will execute the handler exception vector everything in ARM mode. So that is what is the reason why it can't be done. Okay. So now you can only you already read it, so you can read this again. That means only one vector table can be managed, and then it has to be done by one more only. Okay. Now you have one more quiz. Take another 5 minutes. Maybe it may need less than that, but no harm. Take little more time. Don't discuss and then come back. Welcome back. I hope you might have noticed the reason correctly. Okay. Yes, it is a A. Why? See, the above the vector table is 0 to 1 C. It is not reserved for any other purpose. Okay, this location. So instead of putting a branch and then going somewhere, I can execute the FAQ handler here itself. What is the advantage I get? The branch is a waste actually. You know, it actually takes the control to something, and then only actual job is done that in the handler. So effectively it wastes lots of cycle because you know pipeline because of that. So you can as well write the code here itself. So the reason is that why the other reasons are not making sense. All other exception handler need memory space where FAQ handler normally needs a few words. That's not true. Everybody needs space, and you can't decide. No, the program as a developer, system developer, you may decide to put a long routine in the FAQ. You are not supposed to do a long execution there, but it all depends on the program whether you are connecting which particular peripheral to a FAQ interrupt. So you cannot decide on this. Okay. Only FAQ needs faster response time, others don't. It's not true with either. Reset needs a much faster response too, because that is the highest priority. Okay. But why it is not put here? You are saying that reset is the highest priority, but we have put FAQ here to put the handler just after the table. Why? Because reset is a very catastrophic event. Once this happens, you have to react to it immediately, but it is going to take its own sweet time to complete the initialization handler and all the job that you need to do. So it is much more than this one branch instruction. Okay, whereas FAQ is going to be more frequently encountered when you have your system running in that processor. So you want a faster response for the FAQ than a reset. That's the reason why they chose that FAQ has to be in the top. Execution of exception handlers will be slower if all the handlers are placed in the vector table. That is not true. It is not that if you execute from the vector table it will be slow. It is the real problem is how much of space I need to allocate for IRQ. Then after leaving out some space I had to put a handler for this. So if I decide that the vector table is split into multiple things, it is like a fragmented space, and you don't know how much space to reserve. So that's why they put all the table in one place, left to the programmer to decide where the ISRs are. So this is also not a valid reason. Okay, very good. Let us. Okay, this is very simple. Reset signal can be generated either on power on, okay, or on irrecoverable error. On receiving reset signal, okay, this is what is done. On receiving reset signal, okay, let me explain you this. You may get a reset signal from anywhere. Okay, you may be in any mode. Okay, I am taking an example where user mode you are executing, your program is executing, and then a reset has happened. Reset is having a 2 registers. Okay, in the reset mode, there is reset is a if you remember, it's a supervisor mode, right? So it has got a SPSR as well as R14, and R13 is also there. R14 is there. It's a link register. So this particular register is loaded with the instruction. Okay, current instruction being not the current instruction, the PC plus 8. Okay, you are executing this instruction plus 8 is what PC is there. That is stored here. Okay, immediately that is stored, and then it jumps to the reset vector. Okay, and then mode bits are changed to supervisor mode, and both are disabled. If you remember, I told you this. T bit is also cleared. Why? because all the exceptions are handled in ARM mode. Please remember, it cannot be executed in thumb mode. So reset can happen when the processor is already in a thumb mode. That time T bit would have been clear. So it is reset. Okay, so it is not in thumb mode, and then forces the PC to fetch the address 00. That is the reset location vector location. So after the reset, all registers except the PC and CPSR are indeterminate. With that, PC you are loading with the value, okay, and CPSR mode bit you are setting, okay, and T bit also you are setting. So that way having a meaningful value. Very good. Now one more quiz for you before we end the class. Please think it over. 5 minutes again. One more 5 minutes break. Welcome back. Now this also option is A. Okay. Why? See, when the reset signal is generated, maybe as a diagnostic purpose, you want to know when the reset happened in the handler. Maybe if it is a power on, it is coming up for the first time. It may not make sense. But if you can sense that the reset has happened not because of power on, but maybe you may have an external circuitry or some more bit to say in the system. Then you want to know what I was doing at the last, just prior to the reset signal came, whether it was doing some which operation. So if it was required, if it is required by the handler, then this value which is stored in the SPSR and R14 of the SVC mode can be used. Okay, I hope it is clear to you. It is only just a diagnostic purpose, nothing else. So what all reset handler does? On entering reset, you do the following: set up other exception vector table entry. So first time, suppose it is power on, remember the memory is having no valid value. So vector table has to be initialized with a branch to the ISR. ISR needs to be loaded in the memory. Please remember, RAM is not loaded when the processor comes up. So it has to be vector table has to be initialized. All the program has to be loaded in the memory. Okay, and then the peripherals have to be set. Programmed to a particular value. Timer, if it has to run, it has to be programmed to run, and then actual code where it is supposed to run. All those things needs to be done. So that is done by what? Then you may wonder if it is not set, what will happen to the 0? Who will set the value with the reset vector? That's a good question. So I will tell you what terminal normally in a system done. This is a ARM system SOC. Okay, what you normally as a system programmer do is you put a ROM or a flash. Okay, which will have the contents even when the power is lost and then when power comes. So initially to start with, maybe the address the 0x will be pointing to the location which is already loaded with some value, which could be a ROM location. Okay, later on you may use a MMU or some circuitry to change this to a RAM location. Okay, this will involve some more knowledge on how the different memories are handled in the system, real system. But for a moment, you can think that in a system, embedded system, on reset, the first reset vector and the code has to be loaded first. It should be available in the ROM, and then what will happen is this code in the ROM will inform the processor to copy it into the RAM, because accessing the code from RAM and running it from the RAM is faster. And then you can also write into data area, you have to keep it in the RAM only. So they are all done in a RAM. So the initial code will be in ROM or a flash, and then after that the control is taken to the RAM, and then the whole thing comes up. So that is why always the first location the reset vector table will be ready. So it will initialize the memory controllers, it will initialize the MMU and cache if it is there, and then the reset controller has to do a stack for each processor. Okay, each mode there is a R13. I said R13 is a stack pointer. Each mode. Okay, they will all have different stack. Okay, I will explain about the stack later on in more detail when I am handling the abort. Right now, you assume that the reset handler does the initialization of each of the R13 of each mode. Each mode is having R13, and they will be initialized to valid stack value. Okay. That means it's an address allocated for the stack of the particular mode. So all the devices have to be initialized, and then copy programs from into RAM from flash or ROM. I told you, and then after that only you should enable interrupt, because if you enable interrupt before initializing the vector table, what happens when it comes to vector table, it doesn't find the proper branch instruction. It will generate another prefetch abort which will not have its own thing. Then the system will never come up. So you have to do all this before we enable the interrupts. So to start with, it will be disabled and then it will be enabled after that in the interrupt handler. Okay, and then user mode, or it will go to user mode or a system mode as you intend to do that. Okay, this is what normally done on a reset handler. Okay, it is not if you understand this much, but later on maybe if you time permits, we will talk more about this. Okay, so we have come to an end of the class today. So we have handled most critical modules. What are vector tables? How they are the ISRs are enabled, and how different banks are used for the vector table, and what are different instructions you can use to jump from vector table to the ISR or handler, and then what are the functions handled by the reset. Okay, so with this we will I'll talk to you in the next class. Have a nice day. Thanks for your attention. Bye bye.